Welcome. In this video, we're going to look at work and energy methods as they apply to rigid bodies. Having previously studied the dynamics of particles, you are likely familiar with the concepts of energy and momentum. These ideas, such as conservation of energy and momentum, have been used to solve problems in particle dynamics. Now that we are concerned with rigid bodies, we need to extend our previous ideas. Just as we have seen that the fact that a rigid body having a finite shape affects the kinematics, that is, the types of velocities and accelerations, as well as the kinetics, such as the fact that the torques can now be applied, we will see that other expressions for energy and momentum and new methods of work are now possible for rigid bodies. This will allow us to determine things such as the power required to overcome a certain amount of friction, or the momentum of a piston head after the combustion stage of an engine, for example. So at the end of this set of videos, you should be able to calculate the work done by a force or a moment on a rigid body. You should be able to evaluate the state of energy of a rigid body, solve rigid body kinetics problems using principles of conservation of energy and the principle of work and energy. And finally, understand that the principle of work and energy is simply another form of Newton's second law. So, let's turn our attention to the principle of work and energy. This was likely introduced to you in your study of particle dynamics. What it states is that T1 plus the sum of U going from 1 to 2 is equal to T2, where T1 and T2 are kinetic energies, and U is the work done by all external forces between points 1 and points 2. So what this states is that the final kinetic energy of a particle is equal to its initial kinetic energy plus the net work done by all external forces on the particle. Do you recall how the above principle was derived? Is this a new law of nature, or simply an existing one expressed in a different form? So let's begin with Newton's second law. Newton's second law states that the net force on a particle is equal to the mass times the acceleration. And I'm not going to add vector forms or anything like that. There's just F equals ma, so let's assume that it's in one dimension. We turn our attention to the acceleration term. So let's look at this acceleration term. We know that A is equal to dv by dt. Similarly, we know that V is equal to the time rate of change of the displacement. If we can eliminate t, eliminate dt from the acceleration and velocity expressions, what do we find? We find that A ds is equal to V dv. Let's isolate the acceleration, so we can just say that A is equal to V dv by ds. And we're going to substitute this in Newton's second law. So sum of the forces is equal to the mass times the acceleration, or the force is equal to the mass times V dv by ds. So we are still dealing with Newton's second law. Nothing has changed here. Okay. Let's rearrange this slightly. So we're going to multiply both sides by ds. So we end up with F ds is equal to mv dv. And as we can see here, we can integrate both sides. So we can integrate the left-hand side over a distance or a displacement s, and integrate the right-hand side between initial and final states of whatever we are looking at, a particle, let's say. So we can say that this is from a displacement s1 to s2, and this would have an initial velocity v1 at position 1 and v2 at position 2. We can assume, and this is a very good assumption, that the mass is constant. There is no change in the mass, no variation in the mass with the velocity. Similarly, well, let's just look at the right-hand side. So the right-hand side is going to be equal to m multiplied by the integral of v dv, which is equal to m v squared over 2, and that will be evaluated between v1 and v2, which is equal to 1/2 m v2 squared minus 1/2 m v1 squared. And this term over here on the left-hand side, it's a force applied over a distance. And this is simply the definition of work, which we denote as U from 1 to 2. Therefore, what we have is the principle of work and energy. On the left-hand side, we have the net work going from position 1 to position 2 is equal to T2 minus T1. And rearranging, we will get our initial form over here. So what we see here is that the principle of work and energy is nothing more than Newton's second law. In fact, what it is an integrated form of Newton's second law, but it is not a new law of nature or anything like that. It is the familiar Newton's second law, but applied over a distance. And again, we haven't answered our question of, well, what do work and energy methods, what does the principle of work and energy look like for a rigid body? So simply, we are recapping ideas from particle dynamics. But now what we're going to see is that for a rigid body, we can have different types of kinetic energy, and also different types of work will be possible. As we just alluded to, the kinetic energy for a rigid body might be different from that of a particle. So let's look at a rigid body here, given in blue. So it's a standard bean-shaped object, fairly arbitrary. And what we're going to do is that we're going to look at particle I, given over here. So particle I is at a distance r from another arbitrary point P. Okay? And this position vector r connecting P to I can be decomposed into x and y components respectively. Okay? And point P, so as we saw in rigid body kinematics, the velocity at point P might be different from the velocity at point I. Okay? Similarly, we have something that might be undergoing general planar motion, so there might be translation and rotation. So I'm including a rotational, a possible rotational angular velocity, omega. Okay, so let's figure out what is the kinetic energy of this generic rigid body in planar motion. So this particle, I, has a mass that we're going to assume is dm, and it is within the body located at point I. Okay, so the kinetic energy of this particle I will just be equal to 1/2 dm vi squared. So this should be familiar. Kinetic energy is 1/2 mv squared. Here we're considering a differential mass, so dm, and that differential mass has a velocity vi squared. Okay, so we can imagine that for the entire rigid body, it will just be a summation of all the individual kinetic energies. Okay, so we could say that this is equal to 1/2 and the integral dm vi squared. And so this is for the entire rigid body. Okay, where an integration, as you know, is simply a continuous summation. Okay, so we need to define this vi. How can we do this? Well, let's assume that we know the velocity at point P. If we know the velocity at point P, we can use relative motion analysis to find the velocity at point I. So the velocity at point I will be equal to the velocity at point P plus the relative velocity of I with respect to P. And we have seen that this relative velocity, it mimics fixed axis rotation. This will be omega, and then the cross product of omega and the position vector r, and this will be r of I with respect to P, which is simply this position vector over here. Okay. So we can express this in Cartesian form. So we can say that Vp is just, we have a x component in the I direction and a y component in the j direction plus omega. And we're going to assume that omega is in the k direction. And this will be crossed with the position vector. And our position vector is just x in the I direction plus y in the j direction. Now, just for practice, I'd encourage you to carry out this cross product yourself. And you will find that this yields the following. So we have Vp x minus omega multiplied by y in the I direction plus Vpy plus omega multiplied by x in the j direction. Okay, now recall that the kinetic energy is expressed in terms of the square of the velocity, right? So it just, as we know, it's just the square of our velocity. We need a product of velocity, and we will use the dot product. And the reason for that is that the dot product yields a scalar. And energy, including kinetic energy, is a scalar. It has no direction. So what we're going to do, we're going to take the dot product of Vi. So we have Vi dotted with Vi. This will give us Vi squared, and without that vector notation, because it just yields a scalar. So all we have left here is Vpx minus omega y squared plus Vpy plus omega x squared. And this is just a result of our dot product where we multiply the individual directions by themselves. So it'll just be the I component multiplied by itself plus the j component multiplied by itself. If we expand this, what we find is that we have vi squared is equal to vpx squared plus vpy squared minus 2 vpx omega y plus 2 vpy omega x plus omega squared, and then we have x squared plus y squared. So what does this tell us? We see here that vpx squared plus vpy squared, this will simply just be vp squared. Okay, so this is just the square, or the summation of the square of each component. So that's just the square of the velocity magnitude at point P. And over here, x squared plus y squared, this will just be our position vector, or our relative position vector, squared. So that's just r squared. So simplifying, we see that vi squared is equal to vp squared minus 2 vpx omega y plus 2 vpy omega x plus omega squared r squared. So this is our expression for the velocity at point I if we know the velocity at point P. And this velocity at point I will go into our integral for the kinetic energy of the entire rigid body. So let's do this. So we have the kinetic energy, T, is equal to 1/2. And then we will have the differential mass, dm, and then multiplied by vi squared. So let's look at each component. So we will have vp squared over here. And then the next term will be minus vpx omega multiplied by the integral over the mass of y dm. So this comes from this term over here, where I've just taken out the constant terms that do not change under the integral, plus vpy omega multiplied by the integral of x dm. And again, this is evaluated over the entire mass of the rigid body, plus 1/2 multiplied by the integral of r squared dm. So let's look at the individual terms. This over here, this integral of dm is just the total mass. This over here, we've seen it before. Okay? So the integral of y dm has to do with the location of the center of mass. Okay? And we've seen that this is equal to y bar multiplied by the entire mass m. Okay, so y bar is the distance between point P and the center of mass of the rigid body. Okay, so y bar m is equal to the integral of y dm. And we've seen this in our study of rigid body kinetics. Similarly, over here, we have x bar m. So this is the distance in the x direction between point P and the center of mass. And then finally, this over here is the mass moment of inertia about point P. And this is a measure of the distribution of the mass about point P. So, what we have here is the kinetic energy for a rigid body, which might be undergoing translation and rotation simultaneously, is 1/2 mvp squared. So this is the kinetic energy evaluated using the velocity known at point P minus the x component of velocity at point P multiplied by y bar m and then multiplied by the angular velocity plus vpy omega x bar m, and then the final term is 1/2 multiplied by the mass moment of inertia about point P multiplied by omega squared. And so this is what we were searching for. We were searching for an expression, the most general expression for the kinetic energy of a rigid body which has a finite shape and mass and could be undergoing general planar motion, which is composed of translation and rotation. So as we can see here, this is much more complex than the kinetic energy for a simple particle, as we have seen in particle dynamics. So what this tells us is that if we know the velocity at point P and the angular velocity, we can find the total kinetic energy of a rigid body using this expression over here. However, and luckily, we have special cases. And here is the special case. If point P coincides with the center of mass. Okay. So if point P coincides with the center of mass, well, what will we have? We have the kinetic energy of the rigid body would be equal to 1/2 multiplied by the mass. And instead of Vp, we would just say that this is Vg, where G is our standard notation for the center of mass. Okay. Now, the next two terms, y bar and x bar. So y bar is the distance in the y direction between point P and the center of mass. Now, if point P happens to coincide with the center of mass, then y bar would be equal to 0. Similarly, x bar would be equal to 0 as well. So the second and third terms would both disappear. And then finally, the last term would be equal to 1/2 Ig omega squared. So instead of the mass moment of inertia about point P, it would be the mass moment of inertia about the center of mass, G. So what we see here is that even in this special case, where point P coincides with the center of mass, we see that we have an additional term. So for a rigid body, compared to a particle, we have an additional kinetic energy term. So what are these terms? This is what we call the translational kinetic energy. And this is what we're used to, this is what we have seen in particle dynamics. The second term here is called the rotational kinetic energy. So with particles, we weren't able to impart a rotation on the particle itself. But with rigid body dynamics, we are able to impart not only a translation, but also a rotation. And there is an energy associated with that rotational motion. And that energy is called rotational kinetic energy. So this applies to general planar motion. Hopefully you see that there is an analogy between the translational kinetic energy and the rotational kinetic energy. So they are both of very similar forms. Okay? So the squared terms are velocity terms. One is a linear velocity and one is a rotational or angular velocity. They both have the multiplier of 1/2 in front of each term. And for the translational kinetic energy, you have this constant, the kinetic energy is proportional to the mass. Whereas for the rotational term, the kinetic energy is not proportional to the mass, but rather the distribution of the mass. And the measure of the distribution of the mass is what we call the mass moment of inertia, I. Okay, so wrapping up, what we have looked at here is, first of all, we looked at the derivation of the principle of work and energy for a particle. Then we asked ourselves, are these terms for work and energy the same for particles as they are for, let's say, a rigid body? So we looked at the kinetic energy for a rigid body by examining the kinetic energy of an individual particle within that body, and then summing over the entire rigid body. And what we find here is that the kinetic energy, in its most general form, for a rigid body, has actually 4 terms. But a special case, if point P coincides with the center of mass, which we will often use in problems, we find that we have 2 forms of kinetic energy for general planar motion. We have a translational component and a rotational component. In the next video, we're going to look at more special cases for the different types of rigid body motion. We will also look at the different types of work that we can perform on a rigid body and compare that to what we can do for a particle.